Okay, so we're going to move on to one last example, ice tables with a twist. So basically these questions just give you a little less information. So let's get into it. The equilibrium constant for the reaction was found to be 0.5000 at a certain temperature. So here we've been given our reaction here, and let's just double check to make sure it's balanced. So 1 nitrogen on each side. We've got 4 oxygens on the reactant side, 4 on the product side, that's balanced, and 1 sulfur on the reactant and product side, so it's already balanced. All right, so if 0.300 moles of SO3 and 0.3 moles of nitrogen monoxide were placed in a 2-liter container and allowed to react. So again, that important word placed, that tells you that it's an initial amount. Okay, and we're looking for what would be the equilibrium concentration of each gas. All right, so let's start off with our balanced chemical equation, same as always. So now we're drawing in the ice table. There we go. Make this line underneath the equilibrium arrow just a little bit thicker so it's easier to separate reactants from products. All right. Now remember, we have to always use moles per liter for all of these values in the ice table. Okay, the question only gives us moles and liters, so we're going to have to do some calculations. So remember that concentration is equal to moles divided by volume. Okay, so let's get this done. Okay, so 0.3 moles divided by 2 liters, that's going to give us 0.150 mole per liter. Same thing with nitrogen monoxide. And since nitrogen dioxide and sulfur dioxide were not talked about, we can assume that both of these are 0 moles per liter. Okay, for the change row, because we start out only with our reactants and no products, we can assume that the reaction or the equilibrium is going to shift to the right to favor the forward reaction, so we can use up these reactants to produce some products. So I'm going to go minus X because there's a 1 coefficient in front of the sulfur trioxide. And I'm going minus X because we got to use up the reactants to produce some products. Then I'm going to go plus X plus X. All right. So what we're doing for the equilibrium row is we're going to be going 0.150 minus X. That will help us to figure out what the concentration is for this. So how I'm getting that is still that I plus C is equal to E. Okay, so the I is 0.150 minus X gives us the equilibrium concentration. Okay, so I'm just writing this in to help us out later. Okay, but the problem is we don't know what X is. So we need to figure that out, and we're going to figure that out using the equilibrium constant. Okay, so that was found to be this number here. Now, the reason why I'm going to rely on the equilibrium constant to help me figure out what x is because none of the columns have enough information where I can use it to figure out what x is. So again, quick equilibrium law expression here. So our products, that was NO2 and SO2. And our reactants are SO3 and NO. So I'm not raising these to any power because all of the coefficients are 1. Okay, so equilibrium constant, that was this number right here. Okay, now remember, equilibrium law expression, you can only put in values from the equilibrium row. So that's why I wanted to write all of these out, so I have something to plug into my equilibrium law expression here. So NO2 and SO2, they were both x, and SO3 and NO were both 0.150 minus x. Okay, so what I'm going to do is I'm going to simplify both the top and the bottom. So for the top, since I have the same thing being multiplied together, I can write it as x squared. For the bottom, same deal. I have the same exact thing written twice, so I can go 0.5 or 0.150 minus x squared. Okay. Then what I'm going to do is I'm going to multiply each side by the 0.150 minus x squared. Okay, so that's going to get rid of these. So then what I have is this. So how I'm going to isolate for x is I'm going to square root both sides. So the square root of this, since the square root and the square cancel out, I can just write it as 0.150 minus x. Now we need to figure out what the square root of 0.5 is. Okay, so it's 0.7071, goes on forever. Okay, so in my next calculations, I'm going to be using the raw unrounded number, and I'm going to distribute this in to this binomial here. Okay, so my number times by 0.15 is going to be equal to that. So 0.1060 goes on forever. Okay, and that's going to be minus 0.7071 goes on forever. X is equal to X. Okay, so now to isolate the X, I'm going to add the 0.7071 over okay, so we've got 0.1060 goes on forever. So now we've got 1 plus 0.7071 goes on forever, so that's going to be 1.7071 goes on forever, X. Okay, and then I'm just going to divide. Okay, so to do this, since for this side right here, all we did was 1 plus the square root of 0.5, that's where this 0.7071 comes from. So what I'm going to do is I'm going to take my answer, and if you have this calculator specifically, you can go divide by, and then you can press the up arrow and select this number here and just go +1. But if you don't have this calculator, what you can do instead is you can just go 1 plus the square root of 0.5, right? Because how we got this number here was we took the 1x and we added it to the 0.7071, and the 0.7071 comes from square rooting the 0.5. Okay, so that's what you could do if you don't have this calculator exactly, and it's not really an option to scroll back in what you've done. Okay, so I get 0.06213 goes on forever. So remember, that's moles per liter. So that is our X value. Okay, so that's important because now we can use it to figure out all of our equilibrium values, and that's what the question's asking for us to find, all of the equilibrium concentrations. So let's figure this out here. So I'm going 0.150 minus 0.0621 goes on forever. Okay, and I'm just going to write that in here because it's the exact same. And then for our products here, NO2 and SO2, these are just going to be just X, so just this value. However, we do need to round it off for the correct amount of sig digs here. Okay, so looking at our sig digs, it looks like the least amount is 3. So if I look at this number, rounding it off for the correct amount of sig digs, 1, 2, 3, this is where my cutoff line would be. So for just NO2 and SO2, the concentration is going to be 0.0621. Okay, and so let's finish these ones here. So 0.15 subtract our answer. That's going to give us 0.08786 goes on forever. Okay, but rounding it to 3 sig digs, counting from the first significant digit, 1, 2, 3, there's my cutoff. So this is going to be 0.0879 moles per liter. Same with this one here. Okay, so even though these were the same calculation, you are expected to show your work. And for ice tables, you are expected to fill it in as much as possible.